First, I want to thank the organizers for the invitation to be here. It's a real pleasure. And I have to say that, like many of you in the room, I am also learning. There's been some great lectures the past few days that I've been here, and you never stop learning. So I am going to talk about El Nino and the Southern Oscillation. And these are the four topics that I want to cover. The first one is just some basic background about the physical mechanisms that give rise to El Nino and La Nina, and also some of their climate impacts. I then want to talk briefly about how we observe ENSO variability, and I'm glad that Johannes talked before me because he covered some of this material, and I'll be able to go through it rather quickly. And then I want to focus on the 2015-16 El Nino, which is a very big El Nino, major El Nino that occurred just in the past year or so. And we'll look at how it evolved in time and some of the dynamical interactions that gave rise to it. And then we'll talk a little bit about how well we were able to predict it. And then the final topic I'll cover is ENSO in a changing climate. So first, El Nino and the Southern Oscillation, or ENSO. This is a year-to-year fluctuation of the climate system that originates in the tropical Pacific. It is generated through interactions between the ocean and the atmosphere mediated by wind and sea surface temperature feedbacks. The warm phase of ENSO we refer to as El Nino, and the cold phase, La Nina. Scientists have been studying this problem for 50 years or more. It is a fascinating problem in Earth system science, and we still don't know a lot about it. We know some things, as I'll show you. But it also, even more importantly, has tremendous socioeconomic consequences, which is why so much effort has been put into trying to understand and predict it. So I want to step through these cartoons just a little bit to give you some very basic dynamical framework for understanding how it works. These are normal conditions in the tropical Pacific, and in normal situation we have a well-developed trade wind system that piles up water heated by the sun in the western Pacific. So we have what's called a deep warm pool. This blue here is the thermocline. It's a sharp temperature gradient region that separates the warm sunlit layer from the cold interior. So you have a deep warm pool in the west. The thermocline is brought up to the surface under the action of these trades through a process called equatorial upwelling. And that creates a cold tongue in temperature that extends from the coast of South America out near the international dateline. In the atmosphere, heated air rises. So you get ascending motion over this warm pool. At mid-tropospheric levels, you have condensation, cloud formation, and precipitation. And then there's a return flow aloft and sinking over the cold water in the eastern Pacific. Now, the atmospheric boundary layer adjusts hydrostatically to the sea surface temperatures so that over this cold water, you have high pressure develop, and over the warm water, you have low pressure. And so we have a situation where the trade winds create an east-west temperature contrast in the ocean. The temperature contrast creates a pressure gradient, and that pressure gradient near the equator, where the Coriolis force goes to zero, basically drives the trade winds down gradient. So these are mutually reinforcing, the SSTs and the winds. So every few years, the trade winds weaken, and when that happens, it allows this warm pool to migrate into the central Pacific. The thermocline flattens out because the trades have weakened. Upwelling still occurs in the eastern Pacific, but the thermocline is so deep now that it's very difficult to bring cold water up, and so we get warm in this eastern Pacific region. Again, with the warmest water moving into the central Pacific, convection follows, and so to the west of this convective center, you have inflow into those rain bands. And so you have a situation where the trade winds weaken, leads to warming, and the trade winds weaken even more. So again, positive feedback that help anomalies in temperature and winds and other variables grow during an El Nino event. And then through negative feedbacks that I'll mention a little bit later, the thermocline is elevated. It reinitiates upwelling in this cold tongue region. The trade winds strengthen, and the system goes into either neutral phase or overshoots into a La Nina phase. So those are some basic principles about how the system works. Just to show you how tightly coupled the ocean and the atmosphere are in the tropical Pacific, I want to show you two commonly used indices. The first one is the Southern Oscillation Index. The Southern Oscillation is this hemispheric seesaw in atmospheric pressure between the Eastern Hemisphere and the Western Hemisphere, discovered by Sir Gilbert Walker in the early 20th century. An index for this Southern Oscillation is Tahiti air pressure minus Darwin air pressure. And this is really a measure of the strength of the trade winds. And so, for example, here, when the trades are strong, Tahiti pressure is higher than Darwin. You have negative wind anomalies in this region here where the gradient in the pressure is strong. Basically, this is stronger trade winds. That's what this negative wind is showing here associated with a positive Southern Oscillation Index. And when the Tahiti pressure is lower than Darwin, so you have a negative Southern Oscillation Index, you have a positive wind anomaly, which is basically flow towards the east. The correlation between these two time series is about 0.9 or more. So that's an atmospheric index, or two atmospheric indices. This is an index we use for sea surface temperature. It's called the Niño 3.4. It's in the central Pacific, where the atmosphere is particularly sensitive to changes in underlying sea surface temperature. We say it's an El Nino when this index is a half a degree Celsius or more for 5 or more months, and La Nina when it's a half a degree Celsius below normal for 4 or 5 months. So the red peaks, these are El Ninos, the blue troughs, La Ninas, and you can see by eye the very high correlation with the Southern Oscillation Index. Again, the correlation between this and these two time series is above 0.9. So this is an illustration of how tightly coupled the system is in the tropical Pacific. Now, of course, what happens in the tropical Pacific doesn't stay in the tropical Pacific, and this is one of the reasons why we are so interested. And when you have these shifts in atmospheric convection, of course, this is heating the atmosphere. Condensation and rainfall releases heat into the atmosphere, and if you move these deep convection centers around, you basically are forcing changes in atmospheric circulation. And these are felt all over the globe. We have atmospheric Rossby waves that radiate out of the tropical Pacific in response to these shifts in precipitation. In the northern hemisphere, there's a pattern called the Pacific North American pattern, and it was discovered about 35 years ago. And it's a series of high, low, high pressure centers that radiate out from the tropical Pacific. There's an equivalent, the Pacific South American pattern, and this is these are most developed in the winter season of each hemisphere. So December, January, February, June, July, August in the southern hemisphere. So we have these radiating atmospheric Rossby waves emanating from the tropical Pacific, and they change the patterns of atmospheric circulation. And here's just an example over North America. So there are two consequences to the Pacific North American pattern. One is that the jet stream, this is the flow at 10,000 meters where the jets fly, it intensifies and it shifts southward. So normally all the weather that would be brought across the center of the United States in the winter season is shifted south. And so typically we have a wet winter in the US during El Nino years. The Aleutian low deepens in the northeastern Pacific, and so the geostrophic airflow around that low brings subtropical air up into the Pacific Northwest where I live, and so we have typically warm El Nino winters. So this is the picture for just the United States or North America, but there's a global fingerprint as well because of these changes in circulation. And this is the December through February pattern associated with an El Nino event. And this is the December through February pattern associated with La Nina. And well, you see some obvious things that during El Nino, the rainfall shifts from the western Pacific into the central Pacific. So you get wet here and along the coast of South America, dry in the Philippines, Indonesia, and Australia. The intertropical convergence zone and the South Pacific convergence zone move towards the equator, and so you get dry in this horseshoe shape. And there are other patterns that you can see as well. Now, when you look at these patterns, it's important to realize that when an El Nino or La Nina occur, you are not guaranteed to see this sort of climate anomaly in these different regions. These are shifts in the probabilities for certain kinds of weather patterns. So you're more likely to see dry here and wet here, but you're not guaranteed. And so, again, think of these as probabilistic statements for different kinds of weather patterns: droughts, floods, heat waves, and extreme events. One very important consequence of El Nino and La Nina is they affect the formation, the frequency, and the intensity of tropical storms in the Pacific and the Atlantic. And so during an El Nino, tropical storms in the Atlantic are suppressed. And the reason is, again, this southward shift of the jet stream. When it exits over the tropical Atlantic, it affects the high-level shear, wind shear, in the main development region for tropical storms. In the Atlantic, storms don't like shear. And so the fact that we've shifted the jet stream south, you tend to suppress Atlantic hurricane formation. The opposite thing happens in the Pacific, though, because there's so much warm water. Tropical storms like water that's 26.5 degrees Celsius or warmer. And so during an El Nino, you've got a lot more warm water. So you get more intense storms, and they range over a larger geographical area. And then the opposite tendencies occur during La Nina. You get more tropical Atlantic storms and fewer tropical Pacific storms. At the end of the 97-98 El Nino, NOAA made an estimate of the net impact of that event on the globe. And this was the tally: about 23,000 fatalities worldwide and economic losses of 36 billion. These are, as US dollars, these are 1999 dollars today. That's about 55 or 60 billion. And most of the economic losses in the developed world, because that's where wealth is concentrated. Most of the fatalities in the developing world primarily through the spread of infectious and contagious diseases like malaria, dysentery, and cholera. So very significant impacts. Now, everyone thinks that El Nino is bad news, but actually that's not the case. And I'll show you for the US, this was one tally of the impacts on the US. The US, according to this author, actually benefited from the 97-98 El Nino. I mean, there were some negative impacts. You could identify fatalities that were directly due to some of the extreme weather events, and $4 to $5 billion in economic losses. But there were some positive impacts as well. Estimate of 850 lives that were saved, and 20 billion in economic gain. So how do you get that? I mean, how do you come up with lives saved and economic benefit? Well, it's easy to understand when you realize that hurricanes are the largest source of damage in the US. I mean, the Hurricane Harvey and Irma this year, $200 billion in damages in Houston and Florida. If you don't have as many hurricanes, you have less chance of making landfall, so you save. It was a very warm winter in the Midwest of the U.S. There are hundreds of lives that are lost from exposure. Those people didn't die in a warm Midwest winter, and there was more commerce because it was warm. People went out and shopped. Of course, everybody is shopping online today, so it's not clear that this would apply in most El Ninos now. But in any case, there are winners and losers. Obviously, those who were affected here are not the same as those affected here. Okay, so that's some just very basic background. How do we observe El Nino and the Southern Oscillation? And Johannes has already talked about this a little bit. We have a global ocean observing system that has been developed over the past 30 years or so, and it consists of a constellation of Earth-observing satellites for variables such as surface winds and sea surface temperature, surface heights, surface salinity, and other kinds of variables. But you need to measure in the ocean as well, because satellites don't penetrate below the surface. And there are some things they don't measure at all. For example, air temperature, they don't measure directly. They don't measure humidity. So you need in situ measurements as well. And our in situ observing system, there are lots and lots of different platforms that we have. We have ships of opportunity. We've got drifting buoys, Argo floats, Johannes mentioned, and we've got some moored buoys. So in this part of the world ocean, the tropical Pacific, we have a very special observing system that we developed in the mid-1980s. It's called we originally called the Tau array. Now we call it Tau Triton array, because it's a combination of US and Japanese contributions. The basic building block of this array is what we call the Atlas mooring. It was developed at my laboratory in Seattle. And it has 4 important attributes that make it really ideally suited for looking at variability in the tropical oceans. 1, it measures every 10 minutes, and we know there's a very broad spectrum of variability in the tropics, from sub-daily to decadal. You can resolve those with moorings if you keep them out long enough. All the data come to shore in real time via satellite relay, so you can feed these data into numerical models or any kind of model for climate prediction. And you can start to look at the data and monitor how the system is evolving day by day. El Nino and the Southern Oscillation are a coupled ocean-atmosphere phenomenon, and you get both ocean and atmosphere from a single platform, winds and other meteorological data from the surface float, and on the mooring line below, you get ocean parameters, temperature, salinity, velocity, and others. And we designed these systems to be low cost, because we needed to cover a third the circumference of the globe at the equator. Moorings traditionally have been very expensive. We stripped these down to measure only the most essential variables. And we made a conscious choice not to go high tech. This runs on flashlight batteries, not solar panels, and it's anchored to the ocean floor with old railroad car wheels, scrap metal. So it took 10 years to build this, and it's been operating reasonably well since then. And we're going to look at the evolution of the 2015-16 El Nino, focusing on these and other data sets as well. So 2015-16, it was a big El Nino. It was in the news constantly for about 18 months, and it had all the classic hallmarks of a big El Nino: droughts and floods and other kinds of extreme weather events around the globe. And in some ways it mimicked the big 97-98 El Nino and the 82-83 El Nino before that. So here's the star of the show. This is global sea surface temperature anomalies for December 2015. And you see this unusual warming from the coast of South America out to the international date line. There are other anomalies on this map as well, none of them quite so large, although there's a big one here in the Gulf Stream. Some of them are, in fact, related to the El Nino. Like this warming in the Indian Ocean is a typical response to remote forcing from the tropical Pacific at the height of El Nino events. Here's our Nino 3.4 time series again, and this goes from 1980 to the end of 2016. Just as an aside, I got my PhD in 1980, so I know each and every one of these boys and girls. And well, you can see by eye. Okay, here's the end of the record, 2015-16. Here's the big one before, 97-98, and here's 82-83. So 3 really big events in this time series. So just to compare them in a little bit more detail, I'm going to cut this record up into 2.5-year segments, and we'll just stack them on top of one another so you can see a little bit more clearly how they compare in detail. And that's here. Now, actually, I'm going back to 1957-58. So there's 15 El Niños in this record. We start July, the year before the peak of the El Nino. We end January, the year after the peak of the El Nino. And then we just put these pieces, line them up together. El Niños typically are best developed in November, December, January time frame in terms of sea surface temperature. You can see that here. The dashed line here, this is our half-degree centigrade threshold. The black line is the average of the 14 El Niños from 57-58 to 2009-2010. And here is 2015-16. The purple line is 97-98, and the blue line is 82-83. So by this measure, actually, 2015-16 was tied with 97-98 for the strongest on record. There are other indices, though, we can look at. This one is, we just shifted a little bit east, a cold tongue index, Niño 3. When you stack them up this way now, it's the same idea, 2.5-year segments of the Niño 3 index. 97-98 is a clear winner on this one. With 2015-16 sort of running third. In some ways, it doesn't really matter. 2015-16 is easily within the top 3 El Niños on record. That's the most important takeaway message. Now, you lose a little bit of detail when you look at those indices. Something that's been a very hot topic lately is this notion of ENSO diversity, which is that not only is it important that we know whether the Pacific is warm or unusually cold, but we know the detailed structures of the warm and cold anomalies. And this illustrates ENSO diversity in terms of the different kinds of patterns that we see. There's actually quite a range of spatial structures associated with El Niños if you look back in time. And 2 endpoints to this spectrum of diversity. One is called an Eastern Pacific El Nino, and 97-98 was an example of that. Basically, the warmest sea surface temperature anomalies are in the Eastern Pacific. But there's another end member, which is called Central Pacific El Ninos. These tend to have their maximum anomalies in the Central Pacific or near the international date line. 2015-16 looked something of a hybrid between these two. It had large anomalies in the Central Pacific and in the Eastern Pacific, but they began to taper off towards the west coast of South America. Now, this idea of ENSO diversity would be a curiosity if it weren't for the fact that the atmosphere actually cares where the warmest water is, and it can affect the teleconnection patterns and the global climatic impacts. The most obvious and immediate impact of whether you have a Central Pacific or Eastern Pacific El Nino is along the west coast of South America. Eastern Pacific El Ninos bring torrential rains and really create havoc in Ecuador, Peru, and Chile. During Central Pacific El Ninos, there's not much signal along the coast, so there's really not much of a concern for these kinds of events. This hybrid was actually didn't have that much effect on South America, so they actually dodged a bullet in 2015-16. Okay, so we want to look at some of these more time series data now in a little bit more detail and kind of look at the 2015-16 El Nino under a microscope. And because something I want to illustrate now is the fact that ENSO dynamics are really governed by multi-timescale processes. At one level, you have deterministic seasonal timescale dynamics, and this involves coupled feedbacks between the ocean and the atmosphere and wind force changes in ocean circulation, kind of like I showed you in those cartoons earlier at the beginning of this presentation. But there's another part to ENSO dynamics, which is very important, which is high-frequency weather noise forcing. This is on time scales of a few days to a few weeks. It tends to be stochastic because you can't predict these on seasonal time scales. Weather events you can't predict on seasonal time scales. And the most prominent form of this high-frequency forcing is what we call westerly wind bursts. And these wind bursts tend to affect the amplitude, the timing, and the duration of individual events. And we'll see the interplay of high and low frequency in just a moment. So we're going to use tau Triton data for this, and just to set the stage, here, 2 Decembers, December 2015 at the height of the event, December 2016, 1 year later. This was the big El Nino. This was a weak La Nina, and you can see the difference in the temperature and the wind patterns. This weak La Nina, well-developed trade winds all the way across the basin. Here's the equatorial cold tongue with evidence of a cold upwelled water in the eastern Pacific. The western Pacific worm pool pinned up against the coast of New Guinea. A year earlier, trades are near normal in this cold tongue region, but as you go further west, they weaken and they actually reverse in the western Pacific. And in fact, what they're doing is they're converging over this 30-degree water, which has migrated from the western into the central Pacific. And there is a very weak cold tongue here, but nothing like during La Nina or normal period. We can look below the surface, and here's that slide, that plot just for reference. Okay, we're looking along the equator and down to 500 meters depth. Here's the weak La Nina in December 2016. You can see the thermocline sloping down. That's because the trade winds are so strong. And worm pool in the western Pacific. 1 year earlier, because the trades have weakened and reversed in the western Pacific, the thermocline is flattened out. There's much less upwelling in the east, and the worm pool has migrated into the central Pacific. And then this is just for December 2015, showing you the anomalies. We saw this before, but here are the anomalies below the surface along the equator associated with this flattened thermocline. You can see a dipole structure, warm in the east, cold in the west. That's basically saying that the thermocline is flattened out. But the other thing to notice here is how big the temperature anomalies are at depth, much bigger than they are at the surface. And this is important because we're going to see that the major source of fuel for El Nino is the subsurface temperature field. Okay, and just for reference, the 20-degree isotherm is here. We often use this as an index for the depth of the thermocline. Okay, so this is probably the most complicated part, but it really does illustrate well the interplay between the high and the low frequency and how these two are really essential for El Nino development. So what we have 5-day anomalies of tau Triton data, and this is why the moorings are so valuable, because you can really pick out the high frequencies here. You would not be able to get this from a ship, and you would not be able to get it from other kinds of measurement platforms that do not sample as frequently as moorings. So time runs down, January 2015, December 2016. This is distance along the equator. Zonal wind anomalies, sea surface temperature anomalies, and depth of the thermocline as measured by the 20-degree isotherm. So a characteristic of all El Niños is that the trade winds weaken, but they do not weaken in a very smooth fashion. They weaken in these episodic, really intense pulses of westerly winds. This El Nino, there were about 10 of these westerly wind bursts, which was a pretty remarkable sequence. And these wind bursts have three important dynamical effects. The first one, so this is outlining these wind bursts. That's the red and the yellows. Very abrupt relaxations of the trade winds. They have three important dynamical effects. One is they cool the Western Pacific warm pool just by evaporation. The winds are so strong, there's a lot of evaporation, and you lower the sea surface temperatures in this western region. The other dynamical effect is that they push the warm pool into the Central Pacific. At the equator, there are no rotational constraints. So if you blow the winds towards the east, the currents immediately accelerate towards the east and can reach very large speeds. And so the currents that are driven by these wind bursts advect the warm pool into the Central Pacific. Here you see the 29-degree isotherm. This is a marker for the eastern edge of the warm pool. And you can see after the repeated and successive forcing of these wind bursts, you can see that 29-degree edge of the warm pool migrating eastward. And so you get warm anomalies in the Central Pacific. And the other important dynamical effect is that these wind bursts excite downwelling equatorial Kelvin waves. And you can see them here. They take about 45 days to cross the basin. In their wake, they leave a depressed thermocline, depressed by 30, 40, or 50 meters, depending on how strong the wind burst was. And you can see several of these in response to those wind bursts. And so the net effect of this repeated high-frequency forcing is to produce a low-frequency signal in surface warming and thermocline depression. So there's a nonlinearity in the system that is intimately linked to this high-frequency forcing. There's another aspect to the low-frequency, high-frequency mix here that I want to talk about. And this relates to upper ocean heat content as a predictor of El Nino. And there's a very elegant theory developed by Fei Jin about 20 years ago, which guides the interpretation of what I'm going to show you here. According to this theory, it says a buildup of excess heat content along the equator is a necessary precondition for El Nino to occur. You can see this satisfied actually quite nicely in two simple time series. One is our Niño 3.4 sea surface temperature index, and the other is a heat content index, which is basically the average temperature anomaly in the upper 300 meters integrated across the basin from the coast of South America to the coast of New Guinea between 5 north and 5 south. And you can see by eye that the red curve, which is the upper ocean heat content, is leading the blue curve, which is sea surface temperature, by about 6 to 9 months. In most cases, not all cases. And so this is, I like to say, if you want to know the future in the tropical Pacific, look below the surface, because that's where the action is. And so this red curve now, this is a useful predictor. You see if it exceeds some threshold, the likelihood for El Nino greatly increases. The biggest buildup of heat content preceded the strongest El Nino on record with 97.98. The second biggest buildup of heat content in this record preceded the most recent El Nino. Now, it's important to note that this buildup of excess heat content is a necessary but not a sufficient condition. It does predispose the system for the occurrence of El Nino, but there have been buildup of heat content in the record before where we didn't get an El Nino, here, for example. The other important element here is the westerly wind bursts. Heat content is sort of like the fuel, but you need to ignite it. You need a match, and the match is the westerly wind bursts. The other important element of this theory, which you can see very nicely, and this is the negative feedback that I referred to earlier, is that El Nino, once it's underway, purges excess heat to higher latitudes, which terminates the event and maybe sets the stage for La Nina. Here you can see that very nicely illustrated during the 97-98 El Nino. As the event is underway, the heat content starts to drop. It's being flushed out to higher latitudes, leaves a large deficit of heat, and that sets conditions favorable for the onset of the 98, 99, 2000 La Nina. So those are some of the negative feedbacks that work against the development of El Nino when you have these positive feedbacks that favor its development. Okay, so a little bit about prediction and predictability. El Nino and La Nina are predictable. They are the most predictable climate phenomenon on the planet, other than the normal march of the seasons. The first successful prediction of an El Nino was made in 1986 by Mark Kane and the group at Columbia University. Now there are about 20 organizations worldwide that routinely make El Nino and La Nina forecasts. These forecast models are reasonably accurate up to 6 to 9 months in advance. And you see this magic number, 6 to 9 months. That's the lead time of heat content below the surface relative to sea surface temperature. The models aren't perfect, of course, and they're, and the predictability, yes, is based on the upper ocean heat content. The models are not perfect. Predictability is limited by this weather noise forcing, these westerly wind bursts, model biases, and errors in initial conditions. And the basic idea here is that you've got data, it's collected in real time, it's fed into prediction models and stepped forward to make a forecast. Now, I realized sitting in the audience the past couple days that I've used a cartoon to talk about forecast models and initialization, whereas we have been inundated with lots of equations about how this works. So I thought I had to show at least one equation, and I took this out of Greg Jacobs' presentation. Okay, so there's the data, okay, Y, and this is a 3D VAR initialization or assimilation analysis step. Okay, so let's look at the forecasts. These are Nino 3.4 predictions from July 2015 initial conditions. And what's shown here is Nino 3.4 on this axis. Time runs on this axis. Each one of these curves is the ensemble mean of a number of different forecasts made by these organizations. These are the 20 or so organizations worldwide that are routinely making these. The squares and the diamonds are dynamical forecast models, and the open circles are statistical forecast models. So this is a combination of the two. Neutral zone is shown here, plus minus a half degree. Above that is a forecast for El Nino. Below that is a forecast for La Nina. And you can see from July 2015, virtually every organization in the world was saying we're going to have an El Nino. And many of them said we're going to have a big El Nino. This was NOAA's evaluation of the observations at that time and these forecasts. There's a 90% chance, greater than 90% chance, that El Nino will continue through northern hemisphere winter, 2015-16, and around 85% chance that it will last into early spring of 2016. So how well did this verify? Pretty good. I mean, it's right in the middle of this forecast plume. And I don't know if you can see it, but the yellow line here, that is the average of all the dynamical models, and the green line here is the average of all the statistical models. The dynamical models actually got it better. This is the first time in the past, since we've been doing this ensembling of different models, that the statistical or that the dynamical models have clearly outperformed the statistical models. And the reason is because the dynamical models have a lot of the explicit physics and nonlinearities built into it, like these high-frequency wind events, whereas the statistical models are based on training using monthly averages going back in time. But it's a pretty good forecast. It's also kind of academic. Not many people live in the Nino 3.4 region. And there are the island states of the Pacific, but what we're really interested in is what happens where people live. And so this is the December, January, February 2016 precipitation forecast from, this is August 2015 initial conditions. This is put together by the International Research Institute for Climate and Society. And for reference over here, this is kind of the historical average of what happens during El Nino events, and I showed this a little earlier. So basically, the browns and the yellows are saying there's a likelihood of below normal precipitation in places like northeast Brazil, Australia, Philippines, Indonesia. Likelihood for above normal precipitation in East Africa, southeast Brazil, and Uruguay. Above average precipitation likely in East Asia and in the island states. Well, actually, that fits pretty well historical expectations. Dry northeast Brazil, wet in southeast, wet in East Asia, and also here, wet along the southern tier of the United States because of that southward shift of the jet stream. That was the expectation. So what actually happened? That's shown here. This is the precipitation anomalies observed in December, January, February 2016. And if you look closely at this, you can see actually some good hits. Northeast Brazil was dry. Southeast Brazil and Uruguay, very wet. East Africa was very wet. East Asia, very wet. It was dry in parts of Indonesia and New Guinea and Australia. Probably the biggest miss was in Southern California. In fact, all along the west coast of the U.S. I mean, there's lots of places where, the hits were good. South Africa was sort of half and half. We expected dry. It was dry in the eastern South Africa, but wet to the west. This is the biggest miss, and this was, everyone was expecting the 2015-16 El Nino to be the great drought buster in California. They had been experiencing 4 years of extreme drought, and they were praying for the rains to come. Well, they came, but they came to my neighborhood, which is not supposed to happen during El Nino. So we had a record wet winter, and it was near normal in California. So, as I was mentioning earlier, that pattern of global impacts of El Nino and La Nina, those are probabilistic. They're expectations, they're not guarantees. And California was an example of where the forecast failed to verify. Okay, the last topic I want to cover is ENSO and global warming. The climate is changing. Is there anyone here who doesn't believe that? Good. The climate is changing, and there are lots and lots of indicators. Here's one that is the most common. It's the global surface temperature over the last 100 and so years, and this is the pattern for that warming. Lots of other indicators as well. Tropospheric temperatures increasing, ocean heat content increasing, sea level rise, disappearing Arctic ice, et cetera, et cetera. Okay? And we know the reason why climate is changing. It's because humans are pumping greenhouse gases into the atmosphere through fossil fuel combustion and deforestation. And this is the iconic Keeling curve. It's risen above 400 parts per million in the past year. And it's very simple physics. CO2 heats the planet. More CO2 heats the planet more. And so humans are the cause. So a major question that has occupied the ENSO community for the last 30 years is, what is the effect of global warming on ENSO? I'm going to summarize 30 years of research in 2 lines. And there are 2 aspects to this, there are 2 parts to this question. The first one is, has global warming affected the ENSO cycle already? And I would say there is no universally agreed on evidence that it has. And the reason is because there is so much natural variability in the ENSO cycle, or diversity, as I was mentioning earlier. Diversity in amplitude, diversity in the spatial structures, diversity in the frequency. There are periods when ENSO events occur more rapidly, like in the first decade of this century, compared to the previous 2 decades when it was once every 4 years or so. We had a period when they were once every 2 years. Lots and lots of natural variability in the ENSO cycle. It's estimated that we need hundreds of years of observational data to pull out with any confidence the fingerprint of global warming or greenhouse gas forcing on ENSO. So it's very difficult to tease those effects out, and I would say no consensus. If there is an effect, it's buried in the noise of natural variability. The other aspect of this is how will it affect ENSO in the future? And for this, well, I think there's a consensus in the community that there is likely going to be an effect on the ENSO cycle. The problem is we don't really know what it is. And the issue is that to answer this question, we have to rely on the big global climate change models, which are good in telling us something about basic trends, upward trends in say, atmospheric temperature. But ENSO depends on a very delicate balance between a variety of different processes, all of which are affected by model resolution, parameterized physics, and how you actually couple the ocean and the atmosphere. And so when you look at ENSO variability in climate change models under various greenhouse gas forcing scenarios 100 years or more from now, they're all over the map. So this is a lot of uncertainty in this question. There is one result, I think, that seems to be emerging, fairly robust, that it's likely that major El Nino events like we saw in 2015, 16, 97, 98, those will increase in frequency. So the big events will get stronger, analogous to what happens with tropical storms. The expectation is the number of tropical storms under greenhouse gas forcing 100 years from now may not increase, but the strong storms will get stronger, mainly because there's more, the atmosphere can hold more moisture in a warmer climate. Okay, so lots of uncertainty here, but there are a few things we can say. One of them is that, let's turn this question around, ENSO affects global warming. And that's because when an El Nino occurs, heat is released from the ocean to the atmosphere. And so for big El Nino, like we saw in 2015-16, global atmospheric temperatures jump by a couple of tenths of degree Celsius. And so we had 3 successive years of record high temperatures on the globe, partly because, of course, the inexorable rise in greenhouse gases, but also we had this bump up from the big El Nino. There's another aspect to this, which is that even if we can't say that El Nino has been affected by global warming, what we can say is when a big event occurs on a background of rising temperatures, this leads to some extreme climate events. And I'll show you a couple of those. 2015 was a record year for tropical storms in the Pacific. We expect this during El Nino. Well, we expect enhanced storminess during El Nino. 2015 was a record year, partly because there was so much warm water from the El Nino, but that occurred on a background of rising global temperatures. And so this is a study from the Bulletin of the American Meteorological Society. The record storm season in the tropical Pacific in 2015 was caused by El Nino, but it was enhanced by a warming background. Another example, drought over Indonesia and the wildfires. Drought is a natural consequence of El Nino in this region, but against the background of warming temperatures, you had extraordinarily high temperatures during this fire season, and that contributed to the outbreak of extreme wildfire, which had significant health effects in the Southeast Asian region from a cloud of smoke that enveloped the region. Finally, record coral bleaching event in 2015-16 because of, or 14 to 16, because of the unusually warm temperatures in the tropical Pacific superimposed on a warming background state. This was the longest and most widespread bleaching on record. About 40% of global coral reefs were affected. There were other global bleaching events during the big event in 97, 98, and 2009, 2010, but not as extreme or not as long. And so this is the compounding impact of El Nino and global warming. So, to conclude, ENSO is the most powerful and predictable year-to-year climate fluctuation on the planet. Advances in understanding, measurements, and prediction systems make skillful ENSO forecasts possible routinely 2 to 3 seasons in advance. Successful prediction of 2015-16 El Nino and its impacts highlight these advances. And the combined effects of a very strong El Nino and global warming contributed to high-impact climate extremes in 2015-16. So even if we can't find the fingerprint of global warming on the ENSO cycle, the expectation is big El Ninos in the future, compounded with global warming, are going to have more extreme impacts. Quickly, some challenges. Understanding what accounts for ENSO diversity. How is it that the various processes that give rise to sea surface temperature anomalies combine in such a way to produce this wide range of patterns? And this question matters because the impacts are affected by where the warm water actually occurs. I spent the last 50 minutes telling you about how wonderful our predictions were for 2015-16. I could have spent another seminar, 50 minutes, telling you how bad they were in 2014. And this was a busted forecast. Everybody expected 2014 was going to be the big El Nino. This is the forecast plume from, I can't read that, June. This is the forecast plume for June 2014 initial conditions. Virtually everyone's saying it's going to be an El Nino, and some are saying it's going to be a pretty big El Nino. And there's the verification. It fizzled out. And this was, obviously, we have a lot to learn about what the sources of predictability are and the limitations of predictability. And then finally, this big question of understanding how greenhouse gases affect the ENSO cycle. Let's say there's a lot of uncertainty associated with this, but it is a really compelling problem. And so it will continue to occupy our attention for many years to come. And then finally, as I mentioned, El Nino can be good or bad, depending on where you are, at a particular time. And so I decided I was going to look at whether El Nino was good or bad here at the Club Pollença, and I gathered some data. This is on the all-inclusive menu. I have my own opinions about whether El Nino is good or bad at Club Pollença, but I'll let you gather your own data. Thank you.
Thank you very much for this outstanding lecture, Mike. So I'm sure that there are questions, but before that I would like to let you know, students, that if in case you don't know about Mike, you can Google his name, Michael McPhaden, and you will find very quickly his publications. He has many publications in Science, in Nature. He didn't cite them here, but we are very lucky to have one, I think, almost the most relevant expert in El Nino. So please take advantage of that. And we won't leave for dinner until we have questions. So.
Hi, maybe you mentioned it and it skipped me, but is there a relation between the intensity of the El Nino followed by the La Nina?
Good question. No. For example, 1997-98, huge El Nino was followed by very big La Nina. 2015-16, huge El Nino followed by weak La Nina. So La Nina tends to occur on the rebound of El Nino. So you might think, big El Nino leads to big La Nina, but it doesn't always work that way. And that's because it's not just, there's a number of different processes involved. So there's no simple rule of thumb that follows the logic that you're applying. Yeah.
Okay, over here. Thanks, Mike. I'm going to have to update some of the slides in my class lecture about El Nino once I download your PowerPoint. I'm curious about your remarks about there being no signature of a change in El Nino. And I just wanted to clarify, is that strictly the observational record? Because the IPCC fourth assessment made a pretty clear statement that the consensus of the dynamical models is that we were moving into a more El Nino-like state.
I think that was about the impacts, that there would be an eastward shift in the teleconnection patterns associated with El Nino. But I don't think, from our observational record, it's too short to have any confidence that we can tease out the fingerprint of greenhouse gas forcing in that instrumental record. There is a paleo community, and there are some people who think that the 20th century appears to be more energetic than previous epochs. But that is, I would say, somewhat controversial because, the paleo records, you're never quite sure what is being measured, and that's an issue. So, but I would say there's no general consensus in the community at large that climate change or global warming or greenhouse gas forcing has affected the ENSO cycle so far. You will find divergent opinions, but I think the broad consensus would be we can't put our fingerprint on, we can't put our finger on what it actually is if it's there.
Hi, McPhaden. Thanks for the lecture. We don't have any consensus about how ENSO is going to change under global warming, but we have some evidence that the global circulation is changing under global warming. So does that going to, ENSO's impact on the other parts of the globe, is it going to change?
Yes. The teleconnections are being filtered through the atmospheric general circulation. And so even if there's no change in ENSO, if the general circulation at mid-latitudes changes, for example, that will affect the teleconnection patterns that emanate from the tropical Pacific. So you can get effects on the teleconnections without actually changing ENSO itself. I'm sorry.
He's asking if there's any publication on that.
We're working on it. Yeah. Okay. We're working on it. Reviews of geophysics, it'll come out next year.
Thank you for your presentation. My advisor used to call you the emperor of topics. So my question is, I would like to know, after Nino, can we experience the consequences of example? Because in South Africa, we are still experiencing the drought. Yeah, we had a warm winter, and then we are preparing to have drought in February. Thank you.
Right. There can be effects that linger beyond the actual El Nino event itself. There's some obvious ones. For example, those places that burned in Indonesia aren't coming back next year. Those are, it's decades. And I didn't have time to talk about, this would have been another lecture, ENSO impacts on marine and terrestrial ecosystems and fisheries. This is another big topic area, and there you can see, events, El Nino event has, long-lasting impacts on the ecosystem. Probably the most classic example was the collapse of the Peruvian anchovy fishery in the 1970s. That was a combination of issues. One is it was being overfished anyways, so it was on the brink of collapse, but then you had this big El Nino come by, and it shut down primary productivity, and it wiped out the fishery for 20 years, basically. So there can be lingering effects. There are nonlinearities in the system that can cause the impact of a single event to persist for many, many years.